In this last lecture about stars, we need to look at this question. Are all the stars we see in the night sky like our sun? So after all we've discovered about stars so far, this should really be an easy question. No, many of the stars we see in the night sky are incredibly different from the sun. There are differences not only in size, but also in temperature, color, luminosity, energy, and many others as well. Here is a star cluster called Omega Centauri. Naked eye, it looks like a single star, but it's actually a collection of perhaps 10 million stars. Just from this image, you can see differences in size, color, and brightness. The extremely bright red and blue stars are much more luminous than the other stars. And as all these stars are approximately the same distance from Earth, the differences in brightness you see are accurate. The apparently dim stars really are dim, and the bright ones really are bright. We aren't biased by different distances. Stars with different colors indicate that they have different surface temperatures. The blue star, labeled at B, is the hottest. The more yellow star, labeled at A, is not as hot, and the red star, labeled at the C, is the coolest of them all. Keep in mind, though, that even a cool star is several thousand degrees. Color is an easily distinguishable feature that gives us some information about stars. What else is there that we can measure? We can actually use the equations we looked at in the third lecture of this unit to determine a lot of information about stars. Here you see a graph called the Hertzsprung-Russell diagram, often just called the HR diagram for short. You have an assignment that goes along with this graph following the lecture. The graph is charting surface temperature in degrees Kelvin or Celsius on the bottom axis as compared to the luminosity or brightness of the star up the y-axis. Notice the numbers on the scale. On the y-axis, the brightness units are made in comparison to the sun. That means anything on the line of luminosity equals 1 is equally bright to the sun. See the sun on that line as well? Anything that falls on the graph above y equals 1 is brighter than the sun. Anything lower on the graph is dimmer than the sun. Sometimes other brightness scales are used. On the x-axis, notice that as you move from left to right, the temperatures decrease rather than increase. It will be crucial that you remember this, as all HR diagrams are set up this way. The axes are also logarithmic, meaning that they're set up in powers of 10 rather than being equally spaced. What you will see is that once the graph is constructed, there are 4 main types of stars. The long diagonal from upper left to lower right is called the main sequence. Remember that these are stars in their hydrogen burning phase. Below that line are the dim, dying white dwarfs. Above the main sequence lie the giants and the supergiants. Neutron stars are not on this graph, as they are not actively fusing stars, but are stellar remnants left behind after their supernova explosions. Also notice that the vast majority of stars are these very small red ones on the main sequence. Here is another HR diagram. The banana superimposed over the main sequence shows what is often termed as the peeling off of stars from the main sequence as they transform into giant stars as they near the end of their lives. Notice that across the bottom, we see a different x-axis scale. Though the temperature values are not listed, those letters are still indicating temperature ranges. The color of each box indicates the color of that type of stars. Remember the dorky sentence I gave you in the third lecture so you can learn to remember the letters in order? The letters from left to right are O, B, A, FGKM. And the dorky sentence is, "Oh, be a fine girl or guy, kiss me." The L and T stars to the far right are not truly stars, but brown dwarf objects that never had enough mass to start fusion. Up the y-axis side, you can also see a different scale for luminosity. This time, they're just giving you the absolute magnitude numbers rather than brightness as compared to the sun. Please notice the direction of the numbers, as this is also crucial. The larger numbers toward the bottom of the graph are dimmer stars. As you move up the side, the numbers get smaller, approaching 0. Then you go into the negatives. Stars with negative absolute magnitudes are extremely bright. Normally, you'd think smaller is dimmer, but it's exactly backwards. You will have a set of questions on your Unit 3 test. It will be imperative that you understand that a bigger absolute magnitude number is a dimmer star, so be sure this is clear in your mind. The HR diagram is a diagram showing stellar luminosity and temperature. It is not a map. It is a helpful way to see how stars change over the course of their lives. Again, we're plotting temperature, which is indicated by color, against luminosity, brightness, as compared to the sun. Here's another version of the diagram, which may be easier to read as there's somewhat less information given on here. Notice how the colors change as you move across the chart. You move from blue to blue-white to yellow-white to yellow to orange and to red. You can also easily see the differences between the 4 groups in terms of size. The small white dwarfs, then the large giants, and extremely large supergiants. Notice how many more stars appear as main sequence stars than giants and supergiants. See also, these small to medium main sequence stars get larger as they get brighter and hotter. Most stars are on the main sequence because that's where they spend most of their lives. Remember that a star the size of the sun can fuse hydrogen into helium in its core for billions of years. But the later stages don't last nearly as long. The sun, though, is a very average star. Can you see the yellow dot representing the sun in this graph? It's right on the luminosity equals 1 line, as the scale is comparing capital L luminosity in terms of luminosity of the sun. And across the bottom, you can see that the sun is a little over 5,000 degrees K. Keep in mind that to the left of 5,000 is more than 5,000. The temperature scale goes backwards. And that the sun is a G-type star. Notice that the sun is in roughly the middle of the graph and is very average in terms of both temperature and brightness. In this one, they label several of the stars that we have talked about so far. Betelgeuse and Rigel, the brightest stars in Orion, and Deneb, the tail of the swan, are all supergiants. Though Betelgeuse is reddish-orange, Deneb is white, and Rigel is bluish. Polaris is a yellow supergiant. Sirius in Canis Major and Proxima Centauri, the closest star to the sun, are both main sequence stars, though Sirius is both hotter and brighter than the sun, and Proxima Centauri is much cooler and dimmer than the sun. Alpha Centauri is very similar to the sun, although slightly brighter. None of the stars we've talked about yet are white dwarf stars, as those stars are so dim that you would need a telescope to see them. Here is that Omega Centauri cluster again. Since these stars are all part of the same cluster, they are all relatively the same distance from Earth. Notice not only the variety of colors, but also the differences in size and brightness that you can see, just from this one image. To activate the animation, click the link at the bottom of the PowerPoint slide. Here, I'll explain briefly what the animation shows. The producers started with the full image of the cluster in the top left image. They then sort the stars by color, moving the blues and whites to the left, the yellows and the reds to the right. This animation of the stars shows that you can actually create an HR diagram from just this one star cluster. Here, you see the main sequence. White dwarfs down here are almost too dim to see in this photo, and these branches of stars are the ones that are peeling off to become giants and supergiants. Notice that the sun is sort of in the middle of the diagram. Drawing lines through the sun, we can split the diagram into 4 quadrants. In each quadrant, stars would be similar to each other as compared to the sun. All stars in the top left quadrant are both hotter and brighter than the sun, while stars in the top right quadrant are brighter than the sun but are cooler than the sun. Make sure that you understand the patterns that we see in stars from this diagram based on where a star falls on it. For your exam, you won't have to draw an HR diagram or know specific information about any one star, but the patterns are important. You'd need to know that the hotter stars are on the left, while the cooler ones are on the right. Brighter ones fall higher on the graph than the dimmer ones. The main sequence stars fall along this diagonal. Giants over here, supergiants up here, and white dwarfs down here. Let's revisit a bit about stellar size. We've discussed already quite a bit about how much larger the sun is than Earth, Jupiter, and the rest of the planets. Now here you see the Sun and Sirius, both main sequence stars, as much smaller than Pollux and Arcturus, which are both giant stars. Now, notice how small giant Arcturus looks compared to the supergiants Betelgeuse and Antares. You may recognize a lot of these names as those of stars we've already talked about in this class. So does that mean that lots of stars are giants and supergiants? Actually not. Only about 1% of stars are giants or supergiants. About 9% are white dwarfs. Most stars are healthy, stable, main sequence stars. If we set aside dwarf and giant stars, let's look a bit more closely at those main sequence stars. Only about 7% of them are yellow or white, similar to the sun. Another 4% of them are incredibly hot blue stars. The vast majority of stars, 79%, are relatively cool red stars. So why then, we look at the sky, do we not see hundreds and hundreds of red stars shining back at us? Why do they mostly look white? The reason is that cool red stars are difficult to see. We can see the blue stars because they are so incredibly hot and luminous. We can see the giants and supergiants because they are so large. Dwarfs and red main sequence stars are so dim that they are hard to spot without telescopes or other equipment. Let's look at Orion as a representative constellation. Even though there are dozens of naked eye stars in Orion's borders, the one we usually see and connect together are these 8 stars. 7 of them are giants, and the star at Orion's head is actually a cluster of several stars. We see the ones that are easy to see. Now here's a simpler example. First, count the number of elephants in the room right now. Easy, right? 0. They'd be really easy to spot. Now, count the people. And unless you're listening in a really crowded place, it's probably relatively easy to count the people around also. What about the insects? That would be a lot harder because they're small and can hide easily. And if I asked you to count the number of bacteria, you couldn't, even if you had a microscope. It would be just too hard to see those small organisms. Same thing with the sky. Remember this picture we looked at earlier? Orion's Betelgeuse is so big that if it was put in the sun's place, Mercury, Venus, Earth, Mars, and Jupiter would all be within Betelgeuse. Betelgeuse is incredibly far away, but it is so large and bright, it is still easily visible to us hundreds of light years away. These giant stars, also called red giants, since most of them are red in color, are very luminous for their size, and these stars are 10 times the size of the sun. Still, they're at a much lower surface temperature, only 2,000 or 3,000 degrees, where the sun is over 5,000. These stars are in the stage of their life where they have expanded in size as they head toward their deaths. Supergiants are even larger than giants, perhaps 100 to 1,000 times the size of the sun. There are even another class of stars called hypergiants, but we know very little about these most massive stars as there are so few of them. These stars will end their lives in a supernova explosion. And finally, the white dwarfs are those small, Earth-sized remnants of a dying star that was about the size of the sun during its life. Though they still radiate a lot of residual heat, they are very dim due to their small size. These white dwarfs will become black dwarfs when they are no longer emitting light. Here is a Hubble Space Telescope image of several normal stars with a few dim white dwarfs visible as much dimmer objects between them. These white dwarfs are often surrounded by planetary nebulae. As the white dwarf dies, it sheds its outer layers, creating intricate patterns of gas. This one is called the Ant Nebula. Here is another color-coded image of the HR diagram. As you look at the individual stars, note the differences in both size and color. And remember that the farther up the diagram, the brighter the star, and the farther down the diagram, the dimmer the star. And in this last image, you see an image from earlier in the presentation repeated again. This time, I want you to notice the numbers going up the right side of the diagram. At the top, you see 100,000 years going down to 1, 10, and 100 million years, down to 1, 10, and 100 billion years, and finally 1 and 10 trillion years. The bigger and brighter the star, the shorter its lifetime. Think of it like a car with a gas tank. The bigger and heavier the car, the faster it burns through its fuel. So a star like the sun is small enough that it will last about 10 billion years. But the largest stars will only survive for several thousand years. These smallest red dwarfs can live for 100 billion years. And since the universe has only existed for about 13 billion years, no star of this size has ever died yet.